Hi, my name is Dana Polstein, and I'm an academic product manager at National Instruments. Today, I'm going to present the NI solution for creating engaging and effective learning experiences for students in mechatronics education. Let's start by discussing the importance of mechatronics education and defining what mechatronics education is. Systems are everywhere. At NI, we're involved in cutting-edge industry engineering applications all over the world. As we work with customers on a global scale, we're noticing that the engineering world is becoming more and more centered on systems and that systems are becoming more complex. Let's take, for example, the automobile. The earliest design of the automobile was a purely mechanical system consisting of a steam engine design. Later, electrical systems were integrated with the mechanical systems with the invention of the internal combustion engine, which required an electric starter. This led to other electric features such as lighting in a car. Next, computers and digital protocols were integrated for onboard diagnostics and other programmable features. And most recently, intelligence have been integrated to allow for driver assistance and even self-driving cars. As you can see, cars have drastically increased in complexity over time as more disciplines of technology were integrated into their designs. As this trend becomes ubiquitous in our society, how can we prepare engineering students to create these designs? This is where NI believes hands-on mechatronics education comes in. Mechatronics is at the intersection of mechanical systems, electrical systems, control systems, and computers. By supplying students with hands-on experience in the fundamentals of individual disciplines as well as the integration of systems, students will gain the skills they need in the workforce. Along with our partners, NI has developed mechatronics education solutions, including hardware, software, and courseware based on our academic platforms, Elvis and myRIO. NI Elvis is a modular laboratory station for teaching students skills. Using top words, Elvis can be customized to teach many engineering disciplines, including mechatronics, circuits, instrumentation, and more. Although students can access the LabVIEW software used in Elvis labs, students are not required to program. This allows them to concentrate on the specific topics presented in the lab without extra complexity. Elvis features hardware and software to give students access to 12 common lab instruments, including an oscilloscope, function generator, and Bode analyzer. It also contains plenty of analog and digital I/O accessed by top boards for lab flexibility. Our second platform for controls and mechatronics education is NI myRIO. myRIO is a student embedded controller for teaching students not only the skills needed in controls and mechatronics, but also how to implement them in designs. It's based on the same technology used in NI industrial embedded controllers like cRIO or SBRIO to prepare students for what they may see in industry. myRIO is designed to be used by beginner through advanced users. The getting started experience allows students to create simple but effective programs quickly. Its open platform and rich features also enable students to complete complex design projects as they become more advanced. With the power of real-time performance and customizable I/O, The possibility for student projects are endless. With our partners, NI has developed Mechatronics teaching solutions in two forms: labs and projects. Lab solutions are turnkey, including the hardware, software, and courseware to equip a full lab. This includes lab stations, full student lab manuals with theory and exercises, instructor manuals, complete software, and more. Alternatively, project solutions are open-ended and can be customized to fit into many different classes. They include resources like hardware kits, open-ended project instructions, and example software. For our lab solutions, we partnered with Quanzer, a leader in controls and mechatronics education. We created 3 types of lab solutions for mechatronics education based on the skills students need to be successful. Students start by learning the fundamentals of embedded programming, sensors, and actuators. As students become more advanced, they begin integrating systems through controls education and then apply them to specialty systems. The NI Quanzer lab solutions feature Elvis with QNet topboards and myRIO with simple to advanced and specialty controls plants. Quanzer has a variety of QNet topboards for both controls and mechatronics. For today, we'll focus on the mechatronics topboards, but be sure to visit ni.com/QNets to learn more. The mechatronics actuators and sensors boards provide the resources needed to learn the basis of mechatronics I/O through hands-on labs. Students apply theory through labs that challenge them to observe, analyze, and draw conclusions. The mechatronics sensors labs introduce students to the most common sensors used in mechatronic systems. The mechatronics actuators labs help students understand the differences among the most common motors used in mechatronic systems and why they're used. Let's do a demonstration of a mechatronics actuators lab. Let's say that a student is learning about DC motors and solenoids. After learning about theory and setting up the hardware, the student will be able to apply the theory and make observations. From the software side, see how a student can change linear amplifier voltage and observe the changes in the motor speed and current. Since the QNet board integrates a solenoid and motors in a small system, the student can also observe the changes that happen after powering the solenoid. Here's how it looks in hardware. Here's an example of a university that successfully outfitted a lab with NI and Quanzer hardware, software, and courseware. This university wanted to ensure that students were engaged and motivated to learn controls concepts, but found it difficult to find lab materials that challenged students to take initiative. They wanted to outfit the controls lab to give students hands-on experience and develop their problem-solving skills. By outfitting the lab with Elvis and QNet topboards, students are now able to complete verification experiments such as the time domain response analysis, frequency domain analysis, stability analysis, and lead compensation, as well as design experiments focused on PID control of motor speed. The next Quanzer NI solution is a Quanzer Cube Servo and myRIO Full Controls Lab. The Quanzer Cube comes with an inertial disc for position and speed control that can be easily switched out for an inverted pendulum. This can be used to teach concepts like swing-up control. Paired with myRIO, students will not only model and simulate control experiments, but will actually do them while taking advantage of real-time performance paired with a high-fidelity control plant. Let's check out a complex but popular control system, the swing-up pendulum. After learning theory in the accompanying lab manual and in the classroom, students will use the Quanser Cube and myRIO with LabVIEW and Quanser Rapid Control Prototyping, or RCP software. As you can see in the right corner, the LabVIEW VI has many components you would commonly see in a controls textbook, such as gains and transfer functions. When the student runs the VI, they can observe and analyze the system components, such as changes in the system as gain constants change. By pairing real-time performance with high-fidelity equipment, students can focus on the controls theory at hand rather than extraneous obstacles they may face with lower quality solutions. They'll also gain exposure to the same technology that they may see in research and industry. While the Cube is the newest plant that Quanser has developed, NI offers over 20 Quanser control plants, all of which can be controlled with myRIO or cRIO, an NI industrial embedded controller. Though the most common use case for the more complex plants is in controls research, Quanser offers full lab courseware for each plant similar to what you saw in the Cube demo. The course material spans from basic PID control taught in an introductory control class all the way up to specialized areas of advanced control. One university where an NI Quanser controls solution was implemented is MIT. In the Department of Aerospace Engineering, Professor Jonathan Howe teaches a feedback control systems course which uses LabVIEW and NI Compact RIO to control the Quanser 3 degree of freedom helicopter. The course benefits from the ability of LabVIEW to run both simulation and control hardware from the same VI, allowing students to get immediate feedback on the difference between simulation and reality. Now that we've explored NI lab solutions, let's move on to NI project solutions. Unlike lab solutions, project solutions offer open-ended project instructions and software that can be modified for different classes. We will discuss projects for Introduction to Engineering, Student Design, and Machine Vision. Pisco Tetrix Prime for myRIO is a great introduction to engineering by giving students hands-on exposure to the basics of mechanical systems, sensors and actuators, embedded control, and programming. The kit includes over 300 Tetrix parts and pieces, several sensors and actuators, a motor board, and more. It also includes a builder's guide, which gives step-by-step instructions for assembling, connecting, programming, and automating 3 Mechatronics assemblies. Students extend the functionality of the base assemblies with Tetrix pieces or other components like 3D printed cars or webcams. Then they program new features with LabVIEW and myRIO. Students can also create new designs of their own. Let's check out what a student might experience after building the rover vehicle. After following instructions to construct and wire the rover vehicle, students configure myRIO for Wi-Fi communication and use LabVIEW to deploy VIs to myRIO's real-time processor. The VIs allow myRIO to communicate with the student's host PC so that they can telenavigate. When the student uses the buttons in the front panel shown on the right, it sends commands to the rover to actuate the DC motors at a certain speed and direction as shown in the video. Since the rover also has an end effector claw and IR rangefinder, students can add on to the open software to easily implement new features in LabVIEW as they learn to program on their own. Senior design is a great opportunity for students to apply the skills they've learned in the classroom to solve real-world problems. Oftentimes, though, making significant progress in a project over a single semester is very difficult when working with complex systems. This is why it's important for students to have plenty of resources for their projects. Along with our partner Digilent, we created these 3 kits to expose students to the most common sensors, actuators, and interfaces they may use in their projects. Along with the kits is the Project Essentials Guide, which provides theory, instructions, software, and a video for using each component. Students can use these projects to simply learn about each component, perhaps even as part of a separate class, or as reference to integrate these components into larger system-level projects. Should students need to extend the functionality of myRIO for their design project, our partners Digilent and Stratum develop boards to add to myRIO. These include a high current adapter, a motor adapter, an NXT sensor adapter, a shield adapter, a CAN bus adapter, and a USB and Ethernet hub. Here's a university that benefited from the Project Essentials Guide starter kits and myRIO in their mechatronics class. At Loughborough University, mechatronics students would often struggle to complete their designs using traditional textual programming languages due to unintuitive syntax and complex hardware integration. Also, after successfully using LabVIEW in their research labs, they wanted to expose students to more LabVIEW to prepare them for research and industry. Loughborough integrated myRIO and LabVIEW into their mechatronics lab. The first 5 weeks are dedicated to learning LabVIEW and myRIO through starter kits and the Project Essentials Guide. The rest of the semester is dedicated to developing vision algorithms and control strategies for a robot table football challenge. This resulted in an unprecedented quality of work afforded by quicker development times that allowed students to develop superior user interface design, sophisticated controls implementations, and a focus on algorithm design. Students were also more engaged, leading to improved grades and positive student feedback. Vision is a hot topic in mechatronics, especially as intelligence is becoming more widely implemented in mechatronics systems. The Vision Essentials Guide enables students to learn vision through real-world system-level projects that apply manufacturing automation, quality control, shape and color analysis, and robotics. Similar to the Project Essentials Guide, it also comes with software and video for extra support. After learning about vision through the project, students can implement the same concepts in their own projects. Here's an example of students who designed an advanced mechatronics systems for student design, a wheelchair that can climb stairs. The students at ETH used myRIO to control wheel balancing, stair climbing, and the transition phases between driving and stair climbing. By using LabVIEW and myRIO, mechanical engineers with little programming experience were able to implement complex controls algorithms. This amazing feat earned the ETH students first place in the NI LabVIEW Student Design Competition. As you can see, NI is dedicated to enabling students to do engineering through mechatronics education solutions. We're excited to partner with you as you develop your new mechatronics curriculum. Thanks for watching.